will be plus. Look, I know the answer, so I know what to fix. Okay, so, but if you do it carefully, you should be able to get this without fixing anything. Okay, so you agree that this, right? So let's see. This is what I would call x. Okay, this is x, right? So d to the dx is going to be equal to d to the dx prime. You have the same problem again?
Should I go and write it down?
Yeah, go and write it, please.
Yeah, so
What is the correct relation?
the correct thing is that means define x prime to be x into 1 plus dl,
Very good.
and then write so let me write here, right?
Yeah.
So then the relation is like I prime of x prime, which
Yeah.
is x into 1 plus dl,
Very good.
should be the scale 1 plus dl
Yeah.
into the scale dimension, which
Yeah.
is minus of scale dimension d minus 2 upon 2.
Minus.
Yeah.
You sure about that?
Because this is the scaling thing, and whatever the scale happen, that is like scale parameter to the power minus of scale dimension
Okay.
to be phi of x.
I think that looks right.
And then if you substitute phi x in terms of here, now in this
Okay.
action, suppose you
Good.
so
So
let
look,
me-
I'll just sit down. Why don't you do the rest of it? Okay, go ahead. You're doing a good job. Thank you. Okay, good. So we solved my problem. Okay, at least I think. Let me work it out and see.
You just
if it
have
actually
power
solves the
from
problem.
that, that's all.
Okay, so this thing is now minus. Right? Okay. And this is also minus. Correct?
Yeah.
Because x
is-
prime,
yes.
so x is x prime and 1 minus dr. That is also correct, right?
Yeah.
Because this is it. Okay, good. Now let us see. So start praying, okay now. So let's see if this works. Alright, so this is x. So x prime is, so if I take d to the dx, good. So let's see what happens. So that's d to the dx prime times to the power of d over here. Okay, good. Then there's a derivative. So you know that the derivative comes opposite to the x. So this is good. Alright. Now the phi has to be written in terms of the phi prime. Right? So now there's a gradient prime. Now phi written in terms of phi prime will be phi prime times 1 plus dl to the d minus 2 over 2 whole thing squared. Okay, because this has to come over here. Now, thank goodness, it all works out. Okay? So the 1 plus dr to the d minus 2 cancels the 1 plus dr to the d minus 2. Okay? Thank you very much. Okay. Alright, good. So we at least managed to get this in real space. Alright, now let's do it for the other interactions. Okay? Because this is a much quicker way, if you get it right, than doing the momentum space. Alright. So basically what you gotta do is just realize that every power of x, okay, so every power of x has dimension minus 1. Okay? Every derivative has dimension plus 1. Okay? Every phi has dimension d minus 2 over 2. Now you just add all those dimensions and you ask yourself what results. Okay, so now let's apply to the m squared term. Alright? So the m squared term looks like m squared integral d to the dx phi squared, right? So let's start counting. So this guy looks like m squared. Alright, now this guy will be a 1 plus dl to the minus d. Correct? Phi squared will be a 1 plus dl to the d minus 2. Okay? Good? So therefore the minus d and the plus d cancel, so this minus 2. So this tells you that in order to keep this thing invariant, n squared dimension has to be plus 2. Because n squared times 1 plus d to the minus 2 has to be invariant. So n squared dimension is plus 2. So it's relevant. Anything that has a positive dimension is relevant. Okay? The coupling. Okay? Now let's look at the 5/4. So it's lambda over 4 d to the dx 5/4. Good. We do the same counting. Lambda, so 1 plus dl minus d, 1 plus dl, 2 times d minus 2. 2d minus 4. So this tells you this must be b minus 4, right? So the dimension of lambda is 4 minus d. And if d less than 4, it's relevant. Okay? Now let's look at some power, 5 to the power 2n. Let's ask ourselves what happens there. So now we can do it very simply. So this is u2n to 1 plus dl to the minus d plus n times d minus 2, right? Because each power of 5 is worth d minus 2 over 2. So this tells me this is un 1 plus dl to the power of n minus 1 d minus 2n. So therefore, the dimension of un or u2n, I don't know what they call it, let's call it u2n, is equal to 2n minus n minus 1 d. Okay? You can easily check that for any n, as long as you're near d equals 4. Right? So let's say n is equal to 3, right? So that would be u to the 6th, 5 to the 6th. Right? So this is 6 minus 2 times d. So anytime you're between dimensions 3 and 4, this guy is irrelevant. And the higher the power, the more and more irrelevant it's going to be. Okay? Fine? All right. Now, this is basically the complete description of the free field switch point.
So,
Yeah.
so why you are saying this positive dimension should be the relevant parameter?
Because the point is that, remember what happened over here, right? This was like the leftover part of all the scaling, right? That was this. So I'm just trying to reproduce it in a very simple way. Okay, I'm saying this guy also scales. I'm trying to figure out how it scales. Okay? The way I try to figure out how it scales is I say this entire thing must remain the same. Okay, whether I rescale it or not. Okay? In order for that to happen, since this thing scales at 1 plus d to the minus 2, this guy has to scale like 1 plus d to the plus 2. Okay? So it's a shortcut to figure out what the dimension is. Similarly, we also did in momentum space. Remember last time for the 5/4 coupling? So same thing, but done much faster. Okay? Good? So that's it. That's it for the free field fixed point. So the free field fixed point in, let's say, dimension 3. In dimension 3, it has two relevant couplings, that is the mass and this guy, and it has one marginal coupling, that is U6. Okay? Good. Now we want to find out what happens when we start adding interactions. Okay, so that's the interesting thing. So let's do it. So now there's a little trick. Okay, so in general, what you want to do is you want to keep as few couplings as possible, right? because keeping other coupling strengths are like hard. I want to keep very few couplings. So I don't want to deal with this U6. Okay, so what do? So I invent a little trick. Of course, I didn't do this. Okay, I'm just saying. Okay, Wilson was the one who did it.
Sir, about
Yeah.
this, for example, the spray field theory, once we have identified the relevant coupling, so
Yeah.
integrating out the higher degrees of freedom, when we have the effective field theory, but this cannot be treated perturbatively. So what do we do?
So RG is perturbation theory, but it's really perturbation theory in the high energy degrees of freedom. So when we integrate out perturbation theory, it's like integrating out everything at once. Okay, you want to calculate some physical quantity, you integrate out all the degrees of freedom and you find the physical quantity. But you can do that only as an expansion in powers of lambda or powers of something else. In RG, you don't integrate out all the degrees of freedom, you integrate out the high energy degrees of freedom. And those guys will have large denominators. If you want to think quantum mechanically, right? When you integrate out and you do perturbation theory, there's always some denominator, right? There's some energy denominator. If you integrate out high energy degrees of freedom, the denominator will be large. And even if your coupling constant is not very small, because the denominator is large, the perturbation theory is valid. Okay? So that's the trick that's being used in RG. You will see how it operates in a minute.
For marginal coupling, that is large, that remains large, right?
Okay, so this is marginal at tree level. Okay, so we don't know what's going to happen to it once you start doing loops. Okay? So, but I don't even want to deal with this. Okay, so what do? So this is Wilson's string. So Wilson says that the dimension of U6, okay, what was it? We just figured it out over there. It was, okay, I have to write it out. So it's 6 minus 2D. 6 minus 2D. Very good. 6 minus 2D. Very good. So the claim is that as long as 3 is less than B, less than 4, U6 is irrelevant. Okay? You agree with that? So the Wilsonian trick.
Why less than that will be
Well, the upper limit is not infinite. But we are going to stay below 4 because above 4 mean field theory is correct. Right? So in this